Okay, let's begin. So, yesterday we saw the definition, the full strength of product structures and ultra product structures. Yeah, so and the transfer principle which makes statements in R and star R, first order sentences in R and star R that are true in both those structures to be exactly the same. Their theories are equivalent. Yeah, that transfer principle is a consequence of Walsh's theorem. Yeah, so we saw Walsh's theorem. Let's recall it quickly. So the interpretation of the term will give me a function which is, these two equivalence classes are actually equal. If you individually like in each structure you interpret that term at appropriate components, then you get a sequence, the tuple, I tuple, and that the equivalence class of that I tuple is same as the interpretation over here. This is a consequence of the definition of ultra product for function symbols and constant symbols. And the next result is, which is the most important result, that for all formulas, these formulas are true in the ultra product structure at a particular tuple of choice functions, equivalence classes of choice functions, if and only if the same formula is true at the component tuples for a large set of indices. Yeah? And as a corollary, we saw that a sentence is true in the ultra product structure if and only if the sentence is true in a large set of indices, index structures. So what we are saying here, very loosely speaking, I also read a document yesterday which said that, they wrote Walsh's theorem, just this version, very informally as saying that a sentence is true in the ultra product if and only if it is true on an average. So you can see that, almost half of the structure, half of the indices, if that sentence is true, then you have this. Yeah, because out of, let's say, when we are talking about natural numbers, then either odd or even but not both will belong to the ultrafilter. So for whatever is the behavior of half of these structures, that behavior, that average behavior is the behavior of the ultra product structure. Yeah, so that's how this is actually an average structure. Okay. Now let us look at one more consequence. If U is principal, so what is the definition? Say U is equal to all those subsets of I such that a particular element belongs to X. So this particular thing is a principal ideal, yeah, because the power set algebra, power set Boolean algebra of a set is atomic. So therefore singleton I naught is an atom. So for some I naught in I, we have this property. Then when will theta be true in the ultra product structure? Then mi modulo u, the product of mi's, satisfies theta if and only if what will happen? The set of all i's, the set of all indices such that mi is true, belongs, theta is true in mi, belongs to u, if and only if what will happen? Like, what is the property for belonging in u? That I naught should belong to this set, right? If and only if I naught belongs to the set of all indices where theta is actually true. So this is if and only if what? What does it mean for I naught to be in this set? Theta is true in M I naught. In fact, you can show something more. So, I mean, you can, so there is a very interesting social choice theory connection here. Yeah, so it has been found recently that ultra products also occur in social choice theory. That suppose you want to think about a voting system for a group of individuals. So they are every voter is allowed to linearly order the candidates. And then there are certain desirable rules that a voting system should have to make it a fair voting system. And if you impose all those results, all those conditions on the voting system, then actually the system turns out to be, I mean, ultimately what comes out of it is an ultrafilter. Okay, so, and because we are talking about a finite list of candidates, an ultrafilter on that set will be principal. Yeah, because every finite Boolean algebra is isomorphic to a power set algebra and hence atomic, and hence this will happen. Yeah, for every finite Boolean algebra, Stone representation theorem will tell you that an ultrafilter has to be principal. And therefore, what turns out of that voting system, that if you try to make it too much fair, then it has to be a dictatorship. And this is precisely dictatorship. So when is the sentence true in the ultra product? If and only if it is true in one of the structures. Okay, so this is called Arrow's theorem. Yeah, normal arrow, bow and arrow kind. Yeah, but this is the name of a person. So if you want to read more about it, yeah, you can. Okay, so in fact, if U is principal, then this ultra product actually turns out to be just that component structure. So using the language of averages that I used here, so every single structure is also an average of this family of structures. And there are more averages. So these averages contain the constituent structures, individual structures, and it contains something more. If we are talking about the constituent structures, then actually they are just mi naught. There is no notion of cardinality or anything, and cardinalities won't change. But usually, if you start with a non-principal ultrafilter, then the cardinality of this blows up. Cardinality of the ultra product blows up. It becomes very much larger. Yeah? We cannot exactly determine what it is. And why is that so? If U is non-principal, then we cannot exactly determine how large it is, but we know it is large. It's Zorn's lemma, yes. So, in order to construct a non-principal ultrafilter, you need to use Zorn's lemma equivalently axiom of choice. So, we do not really have any control over the situation. Yeah, we don't really know what it looks like exactly. We just start with a non-principal ultrafilter and we do this ultra product construction and we know its properties, but we don't exactly know what it looks like. Whether a particular sequence is 0 or not, we cannot tell for that particular non-principal ultrafilter. Okay, so let's say something about that. So, existence of non-principal ultrafilters. So, first thing, recall from Stone's representation theorem. For finite Boolean algebras, or a result just before that, that any ultrafilter on a finite set is principal. Okay, so we already said this. But for an infinite set, we can construct a non-principal ultrafilter. So suppose if I is infinite, let F denote the collection of all cofinite subset of I. So, is this a filter? The set of cofinite subsets of I, is that a filter? Does it contain empty set? No. Does it contain I? Is it closed under finite intersections? Thanks to De Morgan's law. Then it is closed under upper bounds, so all the properties are satisfied. However, it doesn't make decision about every infinite set. Yeah, for example, even numbers and odd numbers, none of them are cofinite. Yeah, they are infinite, co-infinite, so we cannot say that. So this be the Fréchet filter. Yeah, I mean this is the name after this mathematician Fréchet. Then there is a theorem which allows us to extend any filter, any proper filter to an ultrafilter. What do we call it? The prime filter theorem. Yeah, and prime is same as maximal, same as ultra. So therefore, so use the prime filter theorem thanks to axiom of choice to obtain U containing F, where U is an ultrafilter. So I am going to claim that U is non-principal. Can you tell me why? What will happen if U is principal? If U is principal, then it must contain a finite set. And F already contains all the cofinite sets. So therefore, this finite set and its complement are both present, violating the ultrafilter property. Okay, so therefore, this U, whatever U you get, which extends the Fréchet filter, is always non-principal. Okay. So we always know that a non-principal ultrafilter exists. I am not going to write a proof of this. Yeah, you can guess that. Okay. On n, define f tail equal to all those subsets of natural numbers such that there exists an n, capital N, such that for all n bigger equal n, n belongs to x. So this is the tail filter. Why am I calling it a tail filter? Because you can imagine what the condition says. It says that the tail of natural numbers is contained inside such subsets. If you remember, first day I was asking you how to define orders, and then Sufyan said this same exact condition, yeah, that they should agree or they should be comparable eventually. However, this is not entirely the right answer because this is just a filter. It's not an ultrafilter. Okay, so can you verify that this is actually a filter? Is empty set present in here? Every single thing in f tail must contain infinitely many natural numbers. So empty set cannot be there. Then does it contain the whole set of natural numbers? Yes. Is it closed under finite intersections? Because it contains tails, yeah, and then you are taking two different tails. So intersection of two tails is again a tail. So that's also true. Then is it closed under upper bounds? Yes. So all those properties are true, and therefore any filter, in fact this contains all the cofinite filter as well. Yes. So therefore again you can say that any filter which extends the tail filter, any ultrafilter that extends the tail filter is not principal. Yeah. So any ultrafilter U extending f tail is not principal. So on natural numbers we have got two options, Frechet filter and f tail. I mean, in fact they are both equal. Yeah, you can check that. One more way of generating ultrafilters. So if you ever take a topology course, then you will see this particular condition that I am about to write. Let E be a family, a non-empty family, let's say, non-empty family of subsets of I say that E has the finite intersection property It's called FIP, finite intersection property for short. If given any non-empty finite subfamily of E, we have intersection of E prime is non-empty. Okay, so basically what it is saying is simple. So in particular, if you choose E prime to be singleton, then it's saying that that singleton has to be non-empty. You are choosing arbitrary family of subsets. Yeah, it's a non-empty family, but the FIP for singletons will tell you that every single entry in E is also non-empty. Then given any two elements x and y from E, x intersection y is non-empty. If I am given x, y and z, then x intersection y intersection z is also non-empty. Okay, so this is called the finite intersection property. So closed sets in real numbers satisfy this property, closed and bounded sets. I should not say that. Anyway, I don't want to say more about topology over here. Okay, so this is the finite intersection property, and if we are given some family with the finite intersection property, then we can extend it to a filter. If E has the FIP, then it can be naturally extended to a filter. Okay, how do we do that? So define F to be the collection of all those subsets of I such that X contains the intersection of E prime for some non-empty finite subfamily of E. So this is not really a new concept that I am talking about. If you remember, I talked about generation of filters. And in order to generate a filter from a subset, what do you need? You need to close it under finite intersections, and you need to close it under upper bounds. So we are saying precisely that. It already has the finite intersection property, so those finite intersections are non-empty. So these are non-empty, yeah, intersection of E prime, these are non-empty, we are just closing it under upper bounds. So this is a filter. That's your tutorial problem. Okay, so let's not discuss the solution, I will give you some time to try it. So given any non-empty family which has the FIP, it can be extended to a filter, and then thanks to the prime filter theorem, we can extend this filter to an ultrafilter. So every family, every non-empty family with the FIP can be extended to an ultrafilter. Remember this, yeah? So it's a two-step process. The first one is easy and the second one is magic. Let's do a proof of compactness theorem for any satisfiable theory. Yeah, so let L be a predicate language and gamma be a collection of sentences, then gamma is satisfiable if and only if it is finitely satisfiable. So one side is obviously easy. If gamma is satisfiable and M is a model of gamma, then clearly M is also a model of every finite subset of gamma. Nothing hard over there. On the other hand, suppose suppose gamma is finitely satisfiable. So which means for every single finite subset of gamma, there is a model. So let delta be a finite subset of gamma, and let I be the collection of all such deltas. Then by hypothesis, for each delta there is an M delta which is a model of delta. Okay, so for any sentence phi in gamma, let I phi denote the collection of all those deltas which have phi as a logical consequence. Okay? Then the collection E of all these subsets I phi's of I, we are going to claim that it has the finite intersection property. Yeah, so suppose I phi 1, I phi 2 up to I phi n are any finitely many elements of E. Then in particular, I mean, what is the meaning here? Phi 1, I phi 1 is in E, which means phi 1 is in gamma. So delta naught, which is the collection of phi 1, phi 2 up to phi n, that is a finite subset of gamma, which means it is an element of I. Okay? So, and moreover, this delta naught logically implies phi I for each phi I. Therefore, delta naught lies in the intersection of I phi 1, I phi 2 and I phi n. This is very simple set theory, yeah? Nothing hard is happening here. We are just using a bunch of definitions. So the claim is proved that it has the finite intersection property. Yeah, it's always non-empty. Any finite family subfamily has a non-empty intersection. Then we know that we can extend any such family with the FIP to a filter and then to an ultrafilter. Okay? So let U be an ultrafilter extending this family E. Then simply we are going to claim that the ultraproduct is a model of gamma. So let theta be an arbitrary sentence in gamma. We would like to show that the ultraproduct satisfies theta. Yeah, theta is true in the ultraproduct structure. So by Wasch's theorem, it is enough to show that the collection of all those deltas, which are finite subsets of gamma, where m delta satisfies theta, is a large set of indices. Okay, but since theta is in gamma, what do we know? That I theta is in E. And E is a subfamily of U. So therefore, I theta is in U. So it is enough to show that I theta is a subset of the set that we want, this subset. Then since U is an ultrafilter, it is closed under upper bounds. So then everything will be all right. So because delta is in I theta, okay, so delta has theta as a logical consequence. What is the meaning of this, that theta is a logical consequence of delta? It means that for every model of the left hand side, right hand side is also true. So m delta is a model of delta. So therefore m delta satisfies theta. So we are done. We have shown that okay, so maybe I should write one more line, and therefore I theta is a subset of all those deltas where m delta is a model of theta. And therefore, since U is an ultrafilter, yeah, we got that the collection of all those deltas where theta is a model is in U. Any questions? So this is the famous compactness theorem, the original proof that Gödel had. Yeah, that was using his completeness theorem. Yeah, just the way we did it for propositional logic, right? So the same proof he wrote in the case of predicate logic. But because we haven't covered the completeness theorem, we only saw the semantic version, the compactness theorem. Okay. So one simple application of compactness theorem is that you can prove that every single set can be linearly ordered. A simple application, I will do it quickly. So let I be any set, then there exists a linear order on I. Okay, so you have seen a similar statement earlier, the well ordering theorem. But here we are asking for something much less. And it also fits nicely because well ordering theorem is equivalent to axiom of choice. And we used Zorn's lemma, which is also an equivalent of well ordering theorem, to prove compactness via the prime filter theorem. But the prime filter theorem is strictly weaker than Zorn's lemma. So therefore, this statement is also strictly weaker. It just says that there is a linear order. It doesn't say it's a well order. Every well order is a linear order, but we are trying to prove a simpler statement. And how do we show that? So the idea, take a constant symbol C sub A for each A in I. Okay. Then you say the elements and add CA not equal to CB in the theory gamma for each A not equal to B in I. Also add sentences describing a linear order, describing the axioms of a linear order. Then what you need to do is show that this particular gamma is finitely satisfiable. So you can always include the set of axioms of linear order, and only one of the finitely many CA and CBs will be present. So every finite set can be linearly ordered. So therefore, the entire set can be linearly ordered by compactness. You have seen some similar application for coloring of graphs in propositional logic. Yeah, the idea is similar. Yeah, compactness theorem is always applied in the same fashion. We'll see some very strong applications of compactness in the next week in the form of Leeuwenhoek-Skolem theorems. But for today, we'll stop by saying that compactness theorem and ultraproducts are useful, but they are not constructive in nature. You know something is there to work with, but you don't know what it is. You cannot actually touch that structure. You cannot feel it. Okay? So let's stop.